Kia ora. This is a great little simulation by PhET, and we're going to use it to explore solubility equilibria. So if you have a look, I've got my salt in the salt shaker. Nothing has gone into solution yet because I haven't added anything. And so if I now shake my salt cellar, the only source of the sodium chloride is from this salt shaker. And notice that I have equal number of ions of sodium and chloride. It's because the sodium chloride is a 1:1 ratio, NaCl, and that all the Na plus and all the Cl minus only come from my little salt shaker over here. And you'll notice as I add more, then I'm going to start getting some undissolved, and you can see it's dissolved again, so I've got to add a little bit more. And eventually you'll see there'll be a point where I will not have all my sodium chloride dissolving. So I have some dissolved and some undissolved. Now, if you have a look, you'll see that it's not static. It's although the solution will look colorless no matter how much salt I add, and I'll just simply have then some undissolved white solid at the bottom. That's what you would see. But on a microscopic level or submicroscopic level, some of those chloride and sodium ions are going to go into solution and others will come out of solution. So we say the rate of dissolution is the same as the rate of deposition. We've got this constant tug of war going on between the water particles and the ions. So that's the first idea you need to get clear in your mind, which is this dynamic equilibrium between the two. We're going to explore now with slightly soluble salts. So remember we had sodium chloride, which is a 1:1 ratio, and we'll explore now silver bromide. Silver bromide, what do you think its formula would be? If you have a look, you can see it's also a 1:1 ratio of around about 43:43. The simulation isn't absolutely exact. The more substance you add, the better the correlation. But you can see it's also a 1:1 ratio. So my formula is AgBr. The type would be an AB salt because I've got one A cation to one B anion. And we can compare this with another salt. Now, notice the number around about 46 is dissolved. So let's explore copper 1 iodide. Is this more or less soluble? So if I add this, then notice I have more that has actually dissolved. And I also have a 1:1 ratio because it's copper 1 iodide. So it's 1 copper 1 ion to 1 iodide ion. And it's slightly more soluble than the silver bromide. Now, I can only compare the number of ions dissolved for the same type of ion. So I can compare silver bromide with copper iodide because they're both AB salts. But if I now use, for instance, mercury 2 bromide, and I dissolve that, I can't really compare the number of ions now because I'm going to have 2 bromides for every 1 mercury because it's HgBr2. So I'm going to have double the amount of bromides going into solution compared to mercury. And you can see that over here, the bromides are the brown ones and there are more of them than the pink mercury ones. And if I swapped it around, so if, say I have thallium sulfide, this is now an A2B salt because sulfide is 2- and thallium is +1. You can see not very many ions at all in solution, and it's more or less a 2:1 ratio because it's Th2S. So I have got twice the amount of thallium in solution than sulfide. Explore what happens now with strontium phosphate. So if I add the strontium phosphate, I'm trying to add a lot because the more you add, the better the ratios. Notice I have around about 45:30 being dissolved. So that's around about 3:2. And that's because my formula for strontium phosphate is SR3, pure for 2. So I've got 2 phosphates for every 3 strontiums. So you can work out the formula given the values over here, or you could, if you know the formula, know you're going to get 3 strontiums for every 2 phosphates being formed, and you can do the same thing for silver arsenate. So the important ideas over here is, notice that if I have pure water and I'm adding a salt from only one source, my ions are going to be in the same ratio as the formula of that salt. So is it an AB salt, A2B salt, or an AB2 salt? And secondly, that there's a dynamic equilibrium going on with ions dissolving and depositing at the same rate once it's in equilibrium. So have fun exploring. Kia ora.